Hi, I'm Dr. Imogen Whittam. I'm a Hinsey Fellow at the University of Oxford in the UK, and I'm also affiliated with the University of the Western Cape in South Africa. And hopefully you remember me from lecture 9 about picking the right parameters for calibration. This lecture is about flagging your data. And thanks to Joe Callingham and Andre Offringer for slide ideas. So what is flagging? Well, flagging is the process of data editing. So this is getting rid of parts of the data that we don't want. But note that the data isn't actually deleted, it's just marked and then not used in any of the further processing steps. So why do we want to edit our data? Well, some elements might be broken, so we want to get rid of them. Hopefully your antenna isn't quite as broken as the example shown in this image here. Sometimes we get what's known as antenna shadowing, and this is where one antenna is partly blocked by another antenna in the way and can particularly be a problem when you're observing at low elevations. We might have correlator malfunctions at certain time steps. Again, hopefully not quite as dramatic as this example here. Quite often you get an initial pointing delay. This is when an antenna might be slightly slow to get on target. So right at the beginning of your scan, it's not quite looking at the right place. Other problems are things like bandpass issues, or if some antennas are observing at very low elevation, so very close to the horizon, or you might have correlated noise on some baselines. And in all of these cases, you're going to want to remove the data that's affected by these problems, so you're going to want to flag that data. A major reason why we have bad data is radio frequency interference, or RFI, which is a radio astronomer's worst nightmare. So there are two main types of RFI. The first type is made by human activity, normally in the form of communications, because in fact the radio spectrum is almost entirely allocated to services other than radio astronomy. So there are all sorts of other kinds of human activity which are using radio waves to communicate. These are things like FM radio, airplanes communications, satellite downlink, remote controls, digital broadcasts, the list can go on. And these tend to operate on a very narrow frequency range, so only affect discrete bands. The second main type of RFI are more accidental or natural causes of RFI, and these are anything that causes a spark, so things like electric fences, high voltage power lines, the spark in a petrol engine in your car, lightning. These types of RFI tend to be broadband, so they affect the whole frequency range, but they normally affect a very narrow time window. If you think about a spark, that's probably only going to be an issue for maybe a fraction of a second. So what does RFI look like? Well, RFI from human activity, such as mobile phones, air traffic controllers, satellites, tends to cover a very narrow frequency range, and so will appear as a large spike in an amplitude against channel or frequency plot, as shown here. You can see the signal that we want is the wiggles, and then we've got these large vertical spikes caused by obvious RFI. Here's another example where we can see that the RFI causes these horizontal and vertical stripes. And this is because, as we mentioned, most RFI sources either radiate in a very narrow frequency range, like the ones we saw on the previous slide, or they produce a broadband peak in a very short time range, so lightning or some kind of spark. And so in both these cases, they appear as straight lines parallel to either the time or the frequency axis. And so that's why we get this sort of almost grid-like pattern on a time-frequency plot, like we can see here. Here are just some other examples of the sort of patterns that we might get caused by RFI. Here's another example of some pretty ugly looking RFI observations. So what happens if we don't flag? If we've got obviously bad data due to RFI or pointing delays or something, or bandpass errors, and if we just keep all of the data in and then try and calibrate an image? Well, you may well find that you're not able to derive sensible calibration solutions at all. And this is particularly true often of delay or phase solutions. If you are able to derive some kind of calibration solutions and then go on to image, you'll find that your image will be a lot noisier than you were expecting. And depending on how bright your target is, you might actually not be able to see your target at all. And you can see an example of this in the plot here. On the left, we've got the image where all the RFI has been flagged out, and on the right, we've got the image with all the RFI left in, so no flagging. And you can see the image on the right is much, much noisier, and in fact, you can't really identify the target at all, so it's effectively useless for any kind of science. Remember that RFI is not constant in time, so unfortunately you're going to need to flag all of your calibrators and targets separately. So this is a one-slide summary of how we can get rid of all of this bad data. So if we've got any broken elements or antennas, then we need to remove those antennas from the observations. If we've got any correlator mishaps, we need to remove the time steps that are affected. If we've got shadowing, so where one antenna is blocking another one, then we're going to need to remove the antennas for which that's a problem. If we have an initial pointing delay, which is commonly an issue right at the beginning of a scan, we'll need to remove the very first time steps of each scan. And if we've got some bandpass issues, then we'll need to remove the affected channels. We may also have problems with low elevation, so then we can remove the antennas for which the source we're trying to observe is at low elevation. And if we've got problems with correlated noise on some baselines, for example, the low-fast split stations, then we can flag those baselines. So that's all relatively straightforward and can often be done automatically. What's then more of a problem is how we can remove RFI. And I'm going to talk a little bit more about how you can do this in the rest of this lecture. Okay, so you can flag your data in CASA. I think you're going to see how to do this in the tutorials. And the first step is data inspection. So you're going to want to look at the phase and amplitude of each antenna with both frequency and time. And then identify any obvious RFI and remove it. And what's key here is that you really shouldn't be afraid to flag bad data. Corrupted data will hugely reduce the image quality, but the effect of missing data is often relatively minor. So if you're unsure, flag. Note that RFI is a little bit less of a problem with VLBI than it is with a connected array, because you often correlate the RFI away. So with VLBI, your antennas are a long way apart in different countries, often maybe even different continents. And as sources of RFI are normally relatively localized, for example, someone who's left their mobile phone on, With RFI, they may well only affect one antenna. So then when you correlate your signal, the RFI will go away. If you've, however, got a connected array, something like Meerkat or the VLA, those sources of RFI may well affect all of the antennas, so they're not going to go away when you correlate your signals. And just a reminder that flagging is not the same as deleting. We're not actually removing the data when we flag it, we're just marking it to be ignored in further processing. And note that flagging is also not the same as setting your data to 0. It's just marking it to be ignored. So I mentioned that you can flag your data in CASA and that you can do this by looking at each of your antennas and baselines. But with modern radio telescopes, it's not feasible to flag manually. If we take Meerkat as an example, Meerkat's got 64 antennas, which means that there's over 2,000 baselines between each pair of antennas. And if we want to inspect the phase and amplitude of each one with time and frequency, you can see this very quickly becomes completely unfeasible to do manually. So instead, we need more automated ways to flag. There are two main classes of automated RFI removal methods. One is detection, where we find the RFI and then we throw away the affected data. This is what we mean by flagging normally. The second way to try and deal with RFI is filtering or subtraction. And so this is where you estimate the RFI contribution and then try and remove that part and restore the affected data. So the first type of detection methods are what are more commonly used, and there are specialized pipelines to do this for several different surveys and instruments. Filtering RFI is much harder. The resulting data quality is not well understood because if you don't perfectly filter out the RFI, that's obviously going to have an effect on the data that's left over. And this requires a lot more resources. And at the moment, there aren't many or any fully automated filtering pipelines. So now I'm just going to talk a little bit about AO Flagger. This is an example of an automated RFI detection software that you can use with CASA. And it was developed by Andre Offringer. And it flags your data based on statistics. The software can run in a fully automated way, but there's also a GUI that you can use to analyze your results and tweak the strategy. So it's definitely a good idea to play around with this if you're using AO Flagger for the first time. So this flowchart here gives a rough outline of how AO Flagger works. For more details, you can see Andre Offringer's papers, which are referenced on the previous slides. You can rewind this video. So I'm just going to talk through approximately how it works. So as an input, it takes time frequency data. As you can see, an example of that in this slide here, and a single polarization. It then calculates the amplitudes, marks bad channels and times, and then passes this to some threshold, which is a flagging algorithm which identifies the RFI. And details of this are given in Andre Offringer's papers, so check them out if you are interested in the nitty-gritty details. So here you can see an example of the image after it's passed through some threshold, where the yellow stripes show you the data that's been flagged. So then we change the resolution of the data, often by using a Gaussian high-pass filter. We may then continue iterating around this loop. If not, we'll pass it to some threshold for a final time to get our final flag mask. You can see here we've got the bad bits of data that were RFI in our first input marked in yellow. Then we'll combine the flags of all of the different polarizations through to final flag mask that will then be applied to the observations going forward. So one thing to note is that you should always flag first at the highest possible resolution and only average after you've done your RFI detection. And so you can see an example of why that is in this plot here. So on the left, we've got our data at the highest resolution. And then on the right, you can see what this looks like if we average without doing any RFI detection. And so this is a time against frequency plot. And you can see the obvious RFI as mostly horizontal stripes in this image. And you can see that in the image on the right, the averaged one, the RFI is affecting much more of the data than it is in the image on the left. So if we averaged before we flagged, we'd have to throw out a lot more data than if we do the flagging before averaging. So always flag at the highest possible resolution. Flagging is often iterative with calibration. We'll generally apply any standard flags first, for example, due to shadowing or initial pointing delays. Then we'll flag the RFI at the highest possible resolution. You'll then probably average your data and generally then flag again. Then you'll calibrate your data. At this point, you'll inspect your calibration solutions, and you may well then want to do another round of flagging at this stage before you then calibrate again. Okay, so in conclusion, the first step in data processing is data inspection. Then you do your flagging at the highest possible resolution. And this will then probably be an iterative process with calibration. You should make use of automatic flagging routines, although with VLBI, flagging can often be more manual. And if you remember one thing from this lecture, remember that it's better to have less data that is good than to have more data that is bad. So don't be afraid to flag out bad data. Thank you very much.